In this lesson, we're going to look at how to solve exponential and log functions. So these first couple examples are looking at exponential functions. So remember when we have exponential functions and we want to solve them, what we need to do is we need to get both bases so that they're the same so that we can just set the exponents equal to each other. So what I'm going to do is I need to rewrite 32 so that it has a base of 2. So I'm going to keep 2 as is, and 32 I can rewrite as 2 to the 5th. That's going to be something that has a base 2, and when I raise it to the 5th power, it's going to equal 32. So I just simply replace that. And now what I do is I keep this side the same, and this exponent rule is whenever you have a power raised to a power, you just multiply them. So this ends up being 2 to the 5 times x. And now that I have the same bases, in order for this to actually be equal, the exponents have to be equal. So I can set the exponents equal to each other. And now just solve it. So subtract x from both sides. So -1 equals 4x. Divide both sides by 4. We get x equals -1 over 4. So there's my answer. So if I raise 32 to the -1/4, it's equal to saying 2 raised to the -1/4 minus 1. So let's look at the next example. What we want to do for this example is we want to isolate this exponent. So that means I need to bring the 3 over. So first let's start with that. So we have 5 to the x plus 2 equals 21. So then what we want to do is we want to ask ourselves, so now that we have just the exponent on, or the base and the exponent on one side, we want to ask ourselves, what do I have to raise, or how do I rewrite 21 as a power of, or a base 5 to some power? So thinking about that, we know that 5 to the first is 5, 5 to the second is 25. So since 5 to the first and 5 to the second don't give us 21, that tells me that I can't raise 5 to some whole number or even a fraction and be able to get 21. So what we need to do is we need to apply logs here, because I'm asking 5 raised to what power gives me 21, which is essentially the idea of logs. So what we end up doing is we take the log of both sides, and this is going to be a way for us to be able to solve for x, and I'll show you why in a second. So I take the log of both sides, and if you remember, one of the log properties, whenever you have an exponent, that allows you to bring that out in front as a coefficient. So this ends up being x plus 2 in parentheses, because it's the entire thing, times log of 5 equals log of 21. Now, keep in mind, when I said apply log both sides, I automatically chose log base 10 to apply to both sides. I could have done ln of both sides, log base e. You could do log base 2, log base 3, but it's more convenient to do something that you can easily put into your calculator, which is log base 10 or log base e, the natural log. So you would either do ln or log. So then from here, in order to get x plus 2 or x by itself, I'm going to first divide everything by log base 5, or log of 5. So I end up with x plus 2 equals, and I'm not going to put that in my calculator yet because then I end up with the decimal, and it's a lot easier just to write this than to get a decimal, because you don't want to round until the very end. So just make sure that if you do the decimal, you do everything that you see in your calculator. Subtract 2 from both sides. So we end up with x equals log of 21 over log of 5 minus 2. And then if you put that into your calculator, if we do it to like 2 decimal places, we get -0.11. And then a good thing to do here is to check this. Just plug that into your calculator, plug it into the equation, then plug it into your calculator. If you use -0.11 in for x, you're not going to end up getting exactly 24 because this is a rounded answer. You're going to get like 23.9 something. So just know that because you rounded here and you plug it in, you're going to get close to 24, but not exactly 24. Unless you use this to plug in, then you would get exactly 24. So let's look at another one that's similar to that. So this next example, again, we have e raised to some exponent, So first thing you always want to do with these is always isolate that base. So I'm going to divide everything by 3 to get that base by itself. So e to the 5x equals 495 divided by 3 gives me 165. And again, you're asking yourself, well, what do I have to raise e to get 165? So the easiest thing to do is to take the log of both sides. Because we have e, this is going to be more convenient for us to take ln because ln of e is equal to 1. So it's just for convenience. You could, if you really wanted to, do log. As long as you do log base 10 on both sides, it would still work. But like I said, for convenience, I'm going to take the natural log of both sides. So then remember, this allows us to bring that 5x out in front because of the properties of logs. And now this is just going to become 1. ln of e is just 1 because it's really saying log base e of e, and it's asking you e to what power gives me e, which is 1. So it's always going to be 1. So then I have 5x equals ln of 165. Divide both sides by 5 to get x by itself. So we get x equals ln 165 over 5 as an answer. Or if you put it in your calculator, you get 1.021 as an approximate answer. And again, you can check this, and if you're using the approximate answer, you're going to get an approximate, like when you check, it'll be a decimal, versus if you use this to put in your calculator, you'll get an exact answer or an exact check. So now let's look at some equations that have logs already in them. So instead of having to apply logs, let's look at some things that already have logs and see how we solve it. So one property for this is whenever you have a log of the same base equal to a log of the same base, the nice thing is we know that basically what ends up happening is these two pieces are actually equal to each other. So for this one time, I'm going to show you why that's true. But typically, whenever you have a scenario like this where it's log base 4 equal to log base 4, the logs are the same bases, they're equal to each other, and it's just one log on each side, you can really think of it as just cancel out the logs and set them equal. But I do want to show you why that's true. So using the log properties, what you would do is I would subtract this log over. So let's just rewrite this. And I subtract this over, so I get equal to 0. So I just brought it over. Now, using the log properties, we know that we can condense this as log base 4 of x plus 3 over 8x plus 7 because it's subtraction, so it becomes division. And then if you use our idea of drop the log, swing the base, basically just convert this into exponential form. So we have our saying drop the log, swing the base. This ends up being x plus 3 over 8x plus 17 equals 4 to the 0. And we know that 4 to the 0 is just 1. So if I want to solve this, I would cross multiply. So if you ever have a whole number, put it over 1. Then you can cross multiply, and you end up with x plus 3 equals 8x plus 17. And if you remember, what I told you at the beginning is that this is kind of the proof as to why whenever you see a problem like this, you can just drop the logs and set x plus 3 equal to 8x plus 17. So I could have gone right from that beginning step to the step down here, but I wanted to show you why you can. So from here on out, you can now just cancel out these logs if you see one log equal to the other log, as long as you have the same base, because basically we could always go through this process. It's just we don't need to because this is kind of like our proof for why it works. So now that we get down to here, now we just solve it as a normal equation. So subtract x from both sides. We'll subtract 17 from both sides. So those cancel, these cancel. So we have 3 minus 17 gives me negative 14 equals 7x. Divide both sides by 7, we get x equals negative 2. So now when you get into logs though is where you really have to make sure you check. Because if you remember, we can't take logs of 0 or a negative number. So if this answer creates a situation where when you would be taking log of 0 or a negative number, it would come up with a solution that doesn't check. So basically, if I plug in -2 here and it gives me 0 or a negative number, or if I plug in -2 here and it gives me 0 or a negative number, it tells me that my solution wouldn't check because there's a domain restriction on logs. So just make sure that you always check for logs. The exponential functions are always going to work as long as you've done it correctly, but logs, sometimes your answers won't actually work. But in this case, this one will check, so it will be an answer. So just make sure you always check for logs. So I'm going to make a note of that up here. Always check solutions for logs. So you can either plug it in and make sure it works, plug in whatever you get for x and make sure it works, or just think of it as if I plug that in, will it create me a situation where I'd have to take log of 0 or a negative number, and if it does, then in that case it's not going to check. So let's look at some more examples with logs. So this example down here, we have x plus 2 or ln of x plus 2 equals ln of x squared. So like I said, we could go through the whole explanation, but let's just use a shortcut where since it's the same log on both sides, we can just set the insides equal. And in order to solve this, now that we have an x squared, we have to get 0 on one side and factor. So basically, I'm bringing over the x and the 2, so I get this situation. And now we're looking for numbers that add to -1 and multiply to -2. So it's going to be x and x. So we're going to have opposite signs because we're multiplying to a negative. Adding to a negative means the bigger number is going to be negative, so 2 and +1 work. Split it down the middle, so we have x minus 2 equals 0 and x plus 1 equals 0. Bring that over, we get x equals 2, x equals -1. Check both of these. And basically, if I plug in 2 or -1, it wouldn't create 0 or a negative number. So that tells me that both of these are solutions. The other way to check is to actually plug in each and make sure that it creates a true equation. Looking at this next example here, we have a situation where now we just have one log, so we can't just drop the logs and set the two pieces equal because I don't have a log on this side. So what I need to do is I need to create this I need to convert it into exponential form. So when you have the two logs equal, or a log and a log on each side, that's when you can just set the insides equal because of what I showed you. It converts into that, or you convert it into exponential form. So we drop the log, swing the base, so 2x plus 9 equals 2 to the 4th. So we have 2x plus 9 equals 16. Subtract 9. So 2x equals 7. Divide, we get x equals 7 over 2, or 3.5. Make sure you check that. In this case, it does check. It won't create a negative or 0 in the log part. Another case here, for this one, we have ln of square root of x plus 2 equals 1. So remember, ln is really log base e. So I could just rewrite this to start. And then we can drop the log, swing the base. So square root x plus 2 equals e to the 1, which is the same thing as just e. If we want to undo something that has a square root, we would square both sides. So x plus 2 equals e squared. I'm not going to put e squared as a decimal. I'm going to leave it as e squared. And then we would subtract 2 from both sides. So you would have this as an answer, or at this stage, if you want to put it in your calculator, you would have to get a decimal, so 5.389, something like that. So either one of those would work as answers. Again, make sure that you check. When I check this, I wouldn't be taking log of 0 or negative, so it works. Also, if you just plug in the answer, you would get 1 on both sides. So just looking at a couple more here. This example here, if you look, now we have, instead of just log equal to some number or log equal to log, we have a situation where we have log plus a log. So this is where those properties come into play. We really want to condense this first, but we can only do that if these bases are the same. So basically, you wouldn't be faced in a situation where you were given a problem where the bases aren't the same and expected to solve it, because that's the only way we know how to do it. So we can condense these. Since it's addition, it becomes multiplication between these. So x times x minus 7 equals 3. So then, now that I've condensed this, now I can drop the log and swing the base. So I have x times x minus 7 equals 2 to the third. Now I can distribute this, so I get x squared minus 7x equals 8. I'm going to have to factor, so bring that 8 over. So 2 sets of parentheses here. X, adding to negative 7, multiplying to a negative, so we're going to have negative, positive, opposite signs. Bigger number is going to be negative, so it's going to be negative 8 plus 1. Split it, x minus 7, or x minus 8 equals 0, x plus 1 equals 0. So we get x equals 8, x equals negative 1. We need to check both of them. When I plug in 8, I won't get a negative number, so that works. But when I plug in negative 1, right here, it would be taking a log of negative 1, which you can't do, so that one's not going to check. And then this last example here, again, we have a log on both sides, but on this side I have 2 logs, so I have to first condense those. So I'm just going to keep this side the same. And I need to condense these before I can do anything else. So combine these. It's going to be division because it's subtraction between the 2 logs. And now I don't do the drop the log, swing the base because I don't have a log equal to a number. I have a log equal to a log. So now I can just cancel these out by the property that we showed earlier. So x minus 1 equals x minus 1 over x plus 1. In order to solve this, I put this whole thing over 1 and cross multiply. Make sure you have parentheses around these, so you might want to go back and add them here so you don't forget them. So when I cross multiply, I get x minus 1 times x plus 1 equals 1 times x minus 1. And now we have to actually multiply this out. So when you multiply this out, you can use the box method if you want. So we have x minus 1, x plus 1. So x squared, 1x, negative 1x, negative 1. These are going to cancel, so I'm going to be left with x squared minus 1. Some of you like to FOIL, you can do that as well. And then now, since I have an x squared, I'm going to have to factor, so get 0 on one side. So you're going to bring this x over, bring the 1 over. So I get x squared minus x. Those cancel, over here cancels. So we factor by pulling out a GCF of x. And now you're going to split it, set each piece equal to 0, since it's a product of 2 things equaling 0. So this is x equals 0, this is x equals positive 1, and now we check. So when I check, if I plug in 0 or 1, if I plug in 0, I'm going to get negative 1. I can't take a log of negative 1. If I plug in 1, I'm going to get 0, and I can't take log of 0. So basically what ends up happening is both of these do not check. So that tells me my answer is no solution to this, because both solutions I got don't check. And that's it. So remember, log equal to log, as long as they're the same base, you can drop the logs. If you have log equal to a number, drop the log, swing the base. And if you have a situation where you have a log plus a log or a log minus a log on one side, condense those first and then do one of the other two methods.